Welcome! Today, we're diving into the heart of how much of our electricity is generated, the steam power cycle. It's a fascinating journey that takes us from boiling water to generating massive amounts of power. At its core, any power plant is a heat engine. It takes heat from a high-temperature source, converts some of it into useful work, and rejects the rest as heat to a low-temperature sink. The theoretical benchmark for any heat engine is the Carnot cycle. It's the most efficient cycle possible between two temperature limits. Let's quickly recall what it looks like on a temperature entropy TS diagram. The Carnot cycle consists of two isothermal processes where heat is added or rejected, and two isentropic processes where the working fluid expands or compresses. This forms a perfect rectangle on a TS diagram. However, implementing a Carnot cycle with steam as the working fluid is incredibly difficult in practice. Imagine trying to compress a mixture of liquid and vapor perfectly isentropically, requiring a special compressor, or precisely controlling the temperature throughout the entire phase change. It's just not practical. This is where the Rankine cycle comes in. It's an idealized cycle that simplifies the Carnot cycle to make it practical while still achieving good efficiency. The Rankine cycle uses a pump, a boiler, a turbine, and a condenser. Each component handles specific parts of the cycle. Let's look at the main components of a basic steam power plant and how they connect. We have the pump, boiler, turbine, and condenser arranged in a closed loop. Water continuously circulates through these components. Let's map these components onto our TS diagram. We'll start at state 1, where we have saturated liquid water leaving the condenser. First, the water enters the pump, where its pressure is increased. This is an almost isentropic compression requiring work input. Next, this high-pressure water enters the boiler. Here, heat is added at constant pressure, turning the liquid into high-temperature superheated steam. The superheated steam then expands through the turbine. This expansion drives the turbine, producing useful work. Finally, the low-pressure wet vapor enters the condenser. Here, heat is rejected at constant pressure, turning the steam back into a saturated liquid. Now that we understand the processes, let's quantify the energy transfers using the first law of thermodynamics for steady flow systems. This means the net heat and work interactions for a component equal the change in enthalpy of the fluid flowing through it. Let's apply this to the pump. For the ideal pump, we assume no heat loss. For the boiler, there is no work done. The heat added is the increase in enthalpy. For the turbine, the work output is the decrease in enthalpy. And for the condenser, the heat that is rejected is the enthalpy drop. Now we can determine the net work output. This is the turbine work minus the pump work. Alternatively, the net work is also equal to the net heat added to the cycle. The most crucial performance metric is thermal efficiency. It tells us how much of the heat input is converted into useful work. We can substitute our enthalpy expressions into this formula. Another useful way is to express it using the heat rejection ratio. And using enthalpies, this gives us a concise way to calculate efficiency from steam tables. Beyond efficiency, engineers also look at specific steam consumption. This tells us how much steam is needed to produce a unit of power output. It is inversely proportional to the net work output per kilogram of steam. Comparing the Rankine cycle to the Carnot cycle, the Rankine cycle typically has lower theoretical efficiency, but is practically achievable. The Rankine cycle is the foundation of almost all thermal power plants today, powering our homes and industries by harnessing the simple yet powerful phase change of water.